All right, today we're talking about something that could seriously change medicine as we know it. It's called the programmable pill.
So what if medicine could work only where you need it? Just think about that for a second. I mean, no collateral damage, no crazy side effects, just a tiny little package that knows exactly where to go and only activates when it gets there. It sounds like something straight out of sci-fi, right? Well, it's a lot closer to reality than you might think.
But to really get why this is such a huge deal, we have to talk about one of medicine's biggest, most persistent challenges.
See, right now, when you swallow a pill, that drug doesn't just go to one spot. It goes everywhere. It's systemic. It's kind of like trying to put out a tiny fire in your kitchen by turning on the sprinklers for the entire house. Yeah, you'll put out the fire, but you're also going to wreck the living room, the bedroom, everything. That's what happens with side effects. The medicine hits the target, sure, but it also hits a ton of healthy cells, causing that long list of problems we're all familiar with. We desperately need a smarter way to do this.
And that smarter approach, well, it's coming from a really cool field of material science. The answer lies in something called smart polymers. Now, these are not your everyday plastics. You should think of them more like programmable materials. They can be designed to react to super specific triggers in their environment. And for our programmable pill, that trigger is pH, the level of acidity. So these things can just hang out totally dormant until they sense the perfect pH of their target. And then bam, they spring into action.
Okay, but how does a material know anything? How does it know when to activate? To understand that, we've got to zoom way, way in, all the way down to the molecular level. So the core idea is actually pretty simple to grasp. Picture this. You load your medicine into millions of teeny tiny, tightly wound up sponges. These little sponges stay all compressed and closed up until they get where they're going. But as soon as the pH is just right, they suddenly soak up water, swell up, and poof, they expand, squeezing out that drug payload exactly where it needs to be. So what's the actual trigger that makes them swell up like that? Well, it all comes down to a fundamental force of nature, electric charge. Okay, here's the cool chemistry bit. These long polymer chains are decorated with little acidic or basic groups. When the pH changes around them, these groups either grab or lose a proton, and that gives them an electric charge. All of a sudden, all these chains have the same charge. Let's say they're all positive. What happens when you try to push two positive ends of a magnet together? They push apart, right? It's the exact same idea here. This massive repulsion forces the whole structure to uncoil and expand, and that's what releases the drug. Okay, so let's zoom back out for a second. With that basic principle, scientists can become molecular architects. They can build these polymers into all kinds of incredible shapes. You've got tiny spheres, you've got complex tree-like structures, you name it. Each one is like a different kind of delivery truck, custom built for a specific type of cargo and a specific destination. So this is way more than just a neat chemistry trick. We're talking about something that could totally revolutionize how we treat our most difficult diseases. Let's take cancer therapy, for example. It turns out tumors are often more acidic than the healthy tissue around them. So you can program one of these nanocarriers to be perfectly stable at the body's normal pH, which is about 7.4. It just circulates around, totally harmless, ignoring all the healthy cells. But the moment it drifts into the acidic neighborhood of a tumor, where the pH is lower, it activates. It's like a smart bomb, unleashing its chemotherapy payload right on top of the cancer cells and nowhere else. And it's this level of precision that is just mind-blowing. Our bodies are a map of different pH zones. The stomach is super acidic, but then the small intestine is alkaline. By just picking the right polymer with the right pH trigger, you can literally design a pill that survives the stomach acid completely unharmed and then waits to release its medicine hours later, maybe in the intestine or even all the way down in the colon. This tech just blows the doors wide open for new treatments. I mean, can you imagine an insulin pill? One that could actually survive the stomach, freeing millions of people from daily injections? Or what about a Crohn's disease medication that only switches on in the exact part of the colon that's inflamed? That is the incredible promise here. This is programmable medicine. Okay, so this all sounds amazing, right? But the big question is, how close are we to actually seeing these things on the shelf at the pharmacy? Well, the good news is there are already several technologies in the works. One of the most fascinating is a system called CODESYS, that stands for Colon-Targeted Drug Delivery System, and it is a brilliant example of how you can use multiple layers of these smart polymers to get truly pinpoint accuracy.
Okay, check this out. The journey of this one pill it's a work of art. First, there's an outer layer that acts like a shield, protecting it from the stomach acid. That shield dissolves in the intestine, but the drug still isn't released. Nope, there's a second layer, and this one is mixed with a special kind of sugar. It just waits. When the pill finally gets to the colon, the unique bacteria that live there start to eat that sugar. As they do, they create a little pocket of acid right around the pill. And that is the final trigger. That localized acid dissolves the last layer, and the drug is released exactly, and I mean exactly, where it needs to be. And CodeSums is not the only game in town. There are other cool platforms popping up. You have Peptelligence, which is all about protecting fragile drugs. You can take them as a pill instead of an injection. There's Orosome, which uses these tiny pH-sensitive bubbles for delivering hormones. The whole field is just buzzing with innovation right now.
Now look, it's not all easy. There are definitely hurdles. Figuring out how to make these super complex materials cheaply and on a massive scale, that's a big one. You also have to make sure the drug stays stable inside the polymer, and then there's the whole regulatory approval process, which always takes time. But the payoff, wow, the payoff is huge. We're talking about incredibly targeted cancer treatments, an insulin pill, and a future where side effects are the exception, not the rule.
What's really clear is that we are standing right on the edge of a new era in medicine, an era where we can literally program our treatments to be smarter, more precise, and so much safer. So it kind of leaves you with one last question, doesn't it? If you had this technology right now, what's the first disease you would go after?